Welcome to Part 3 in the module that provides an overview of the JAWS web server case study. In previous parts of this module, we started by describing the pattern-oriented JAWS web server case study, and then we described the patterns we'll use in order to be able to rationalize and guide and document the design of the JAWS web server. In this part of the module, we're going to present a pattern language for the JAWS web server and explore various alternative paths through that language. Just to recap a bit, if you go back to section 2 of the course, we had a long discussion about pattern languages. But to recap that briefly, a pattern language is basically a group of related patterns that provide a vocabulary and a process for the orderly resolution of certain types of challenges that arise when you build software in a particular context. If you take a look at this Wikipedia link, you'll find other examples of pattern languages that go above and beyond software. In the particular context in which we're discussing, the patterns in our pattern language will be used to build upon each other to help generate a software architecture and allow us to be able to walk through and navigate the software architecture through successive progressions of design decisions, transformations of the design, and most importantly, different ways of going through alternative paths through the pattern language in the design space. So let's take a look at a number of the different paths we'll be exploring throughout the rest of this section. Here's a high-level view of the pattern language for the JAWS web server. And as you can see, it includes all the patterns that we have summarized in the previous part of the module. Things like wrapper facade, reactor, acceptor connector, and so on. I'm not going to recap these here because we've already covered them. If you need to go back and rewatch that section to get an overview of what they mean, please do so at this point. This particular pattern language for JAWS is also not intended to be comprehensive. There are other patterns you might have to do in order to be able to port this to other environments. There are other patterns you would apply to do other parts of building a web server. And of course, if you build a large-scale concurrent and network software system, there'll be many other patterns you have to deal with in order to address other requirements and environmental constraints. But we'll focus primarily on the parts that relate to the event dispatcher portion, because that's where a lot of the interesting concurrent and network programming issues arise. The first path through our pattern language looks like this. We use the wrapper facade pattern in order to be able to provide a portability veneer on top of whatever operating system platform we happen to want to run on, be it different versions of Windows, different versions of Unix, different real-time operating systems, and so on and so forth. We then apply the reactor pattern in order to be able to handle the arrival of events from multiple sources of events, multiple clients, connection events, data events, and so on and so forth. And then we apply the acceptor connector pattern in order to be able to decouple the event arrival from the connection establishment logic, the service initialization logic, and finally the logic of actually processing the various types of HTTP requests that are sent from clients to the server. This particular solution is very straightforward. It's going to be reasonably easy to implement. It's reactive. Unfortunately, as we'll see, it's not particularly scalable. And that's because there's only one thread of control that's running. And so all the different clients have to be multiplexed and queued up behind that one thread, which could become a bottleneck, obviously, in a large-scale production environment. The next path through the pattern language we'll explore keeps the wrapper facade, reactor, and acceptor connector patterns, but then it adds a couple of more patterns. It adds component configurator to make it possible to be able to dynamically configure the choice of particular implementation details for our web server at late binding time, at installation time, or even at runtime. And we could do this for a whole variety of different purposes. We could add different services, we could change caching protocols, and so on and so forth. And then we're also going to apply something called the activator pattern, which is not in the POSA 2 book, but it's a pattern that's very closely related to the patterns in the POSA 2 book. And we'll use the activator pattern in order to be able to launch the web server process on demand when client requests come along. So this solution is still fairly simple. It's reactive. It's more flexible because we can do late binding of the implementation details of our server. And by using activator, it allows us to have coarse-grained scalability, basically a process per request. The next approach we're going to apply is going to keep wrapper facade, reactor, and acceptor connector, but now we're going to add in the active object pattern. And we're going to use this in order to have a pool of threads that we can run so that each connection that comes in will have one thread dedicated to that connection. By doing this, we keep some of the benefits from before. It's still fairly simple to develop. We now have multi-threaded concurrency, and we'll also be able to get a finer level granularity of scalability by using the thread per connection approach. We'll see as we go forward, though, that thread per connection does have some limitations. If you have lots and lots of clients that are pounding away on your server, allocating a thread per connection can become prohibitively expensive with respect to resources allocated in the operating system. And unless you're willing to go out and dedicate a lot of memory and a lot of horsepower from a processing point of view, you might not want to use thread per connection in all circumstances. So for situations where that doesn't apply, we'll then talk about yet another path through our pattern language design space. This path will use wrapper facade, reactor, and acceptor connector, as we've done before, but now we're going to apply a number of other patterns. We'll apply the HalfAsync pattern, which combines reactor with active object in order to be able to have a pool of threads that work more effectively at mapping the number of cores or CPUs at our disposal to roughly the number of threads we're going to allocate to process requests. We'll use the monitor object in order to be able to synchronize access to a thread-safe queue of requests that sit between the reactive portion and the various active object portions running the separate threads. And then we'll also get a chance to explore a number of synchronization patterns, things like strategized locking, scoped locking, thread-safe interface, and so on, in order to make it easier to synchronize access under the various conditions in which we're applying our web server solution. This approach is concurrent, much more nicely scalable, and bounded scalability tends to work better under heavy loads, for example. The downside is that it's a little bit less predictable because you're allocating memory, you're passing memory between different threads, there's some synchronization overhead, context switching overhead, data movement overhead, and so on. And so in some situations, especially for small requests, this might not be the right way to do the web server concurrency architecture. To address that issue, of course, we'll apply another set of patterns in our pattern language design space. In this particular case, we're going to keep the wrapper facade, but now we're going to skip over reactor and instead apply something called the leader-followers pattern, which is essentially a more powerful multi-threaded reactor that allows a pool of threads to take turns getting the next request from a set of endpoints of request input. And this particular approach, compared to the previous approach, tends to be more efficient and more predictable because there's less context switching, synchronization, and data movement. And you also, if you play your cards right, don't need to have as much dynamic memory allocation. The thread in which the message is received is the thread in which the message is processed. We'll still continue to use acceptor connector with this pattern, and other things will look very much the same, but it'll have other properties. It'll be more predictable than HalfSync, HalfAsync. Then we'll take yet another path through our pattern language. This time, we're going to be exploring the space of asynchronous I/O. We'll keep using wrapper facade to get our portability, but now we're going to be applying something called the proactor. The proactor pattern is a pattern that allows operations to be invoked asynchronously, and as those operations complete, then the proactor will dispatch the completion of the operations to so-called completion event handlers. And they're responsible for figuring out what happened and then doing the next thing, which usually involves spawning additional asynchronous operations. When we talk about proactor, we'll also talk about asynchronous completion token, which is a pattern that's used to very efficiently demultiplex event completion with event completion handlers. This particular approach is concurrent, asynchronous, fairly simple to implement once you have the implementation framework for proactor. It's very scalable on operating systems that support asynchronous I/O, but unfortunately not all operating systems support these capabilities across the board. Windows tends to support them very well. Some versions of Unix do. Other operating systems tend not to. So there's some portability issues with this particular path through our pattern language. So to summarize this section, the pattern language that we'll be discussing here will allow us to be able to navigate through the design alternatives in a systematic way. It'll help us to document what we do. It'll help us to explain to other people the reasons why we chose certain paths through the design space. And we're fortunate that most of the patterns that we're describing here have direct corollary framework realizations in the adaptive communication environment, in ACE. And that'll make it very simple for us to take the patterns and implement them in a reusable way based on the open source capabilities and frameworks and wrapper facades and other components in ACE. And that'll allow us to be able to build JAWS, which is our web server, out of reusable pieces that are open source, that are pattern oriented, and have direct realizations in frameworks that codify the design principles and pattern languages. Take a look at this URL to find out more information about ACE.